Hans Wormhat, this is going to be an introductory video into vision, optics, how the eyes see things, and I don't want to make it too complicated, just ask some really general questions and talk about some very general and obvious ways that the eyes perceive things. So the first two questions that a lot of people don't even think about these ones. Can the human eye see infinitely far? No. Can the human eye see with infinite resolution? Meaning, you know how cameras have a certain number of pixels when you take a picture? Is it like the human eye has infinitely many pixels? And no, it's just not true. And just keep those in mind. Let's get right into it and start talking about optical properties. And what I want to do with this video, at the end, you should have an explanation for really low level your claims that people say, oh, you're living on a ball spinning, hurling through a vacuum, because, and then they just say some optical property. That's just a normal way that optics works on a flat plane. You don't need a curve for any of these things. So here's number one. Two major optical laws. Number one, as objects move away from the observer, they get smaller and tend towards the horizon. And the opposite of that is true. If an object is coming towards an observer, it gets bigger and it goes away from the horizon. Just two pictures illustrating this idea, like a bird flying at you. A bird in the distance is going to be low and small, so low in the horizon, small. As it flies towards you, it gets larger and farther away from the horizon because it starts to be above your head. And an object on the ground, say an apple, as you walk away from an apple, but you're looking at it, it gets smaller and it approaches your horizon. These are just two, or this is the first of two very basic optical properties, the way that seeing objects works. The second one is atmospheric perspective. The farther away an object is, the more washed out the object will look because there's more air between the observer and the object. And there might be a little bit more to this atmospheric perspective of the fact that things lose resolution. Is it entirely because there's air between you and the object? There's probably a little bit more to it than that, but keep it simple. There's just this general idea of perspective where the farther away an object is, the more washed out it gets. And we know this when we look at mountains in the distance. If there's a hill that's close and then a mountain that's farther away behind it, the hill is a sharper image and darker. And then the hill that's behind it, or the mountains that are farther in the distance, they start to get washed out. People paint with these things. Think of, the Mona Lisa is a good example of, they use atmospheric perspective in the background of the Mona Lisa to show you how mountain ranges work. Now, let's do a simple thought experiment. So suppose you live on a flat plane, which you do. You absolutely do live on a flat plane. But this is just the thing. If you do think that you live on a ball Earth, then you still can do a thought experiment where, okay, let's pretend that we're on a flat plane. What would happen? So what would happen if we lived on a flat plane, like we really do? Okay, so let's consider the scenario. We have a 3-foot tall person and a 6-foot tall person, and they're walking side by side away from you at the same rate. Which one do you stop being able to see first? If you have a 3-foot tall person and a 6-foot tall person, perfectly flat, infinite plane that you're on. First of all, if you think that you can see these people forever, that's where you're wrong. The human eye cannot see infinitely far, and the human eye cannot see with infinite resolution. So you're not going to see these people forever. And of course, you see the 6-foot tall person later. The 3-foot tall person is going to eventually become too small. Think of it, you can think of it as the human eye has a certain resolution. It's not perfect. There becomes a point where the 3-foot tall midget is going to be less than a pixel in your vision, but the 6-foot tall person will still be a pixel. Where instead of actual pixel, it's just the ability of somebody to see something with their eye, distance. So what's going on there? Think about that. So how can you still see the 6-foot tall person, but you can't see the 3-foot tall person anymore? That's equivalent to, not being able to see the bottom part of a 6-foot tall person. If you can no longer discern the 3-foot tall person, it's not. So here's the ball earth explanation, would be that 3 feet of visual space is now behind the curve. But if you've done any research into this, you can see NASA claims that make no sense. like seen skylines over huge distances where the skyline should be it should be below the curve, but the curve doesn't exist. And that's when they give crazy explanations about like lensing over the body of water or something. No. It's just you live on a flat plane. The earth is flat and unmoving, just like you experience it every day of your life. Okay, moving on. So, why are people surprised we stop seeing the bottom of objects first? You can't see, let me give you another example. You can't see a 5-foot object that's 200 miles away. You just can't. The human eye can't see like that. You cannot take a 5-foot tall object, move it 200 miles away, and still expect to see it. It's too small, meaning it has collapsed to a point where it's just not discernible from the horizon. Okay, but you could see a 30,000 foot mountain from 200 miles away. If something is big enough, you'll be able to see it from really far away, 200 miles, 30,000 foot mountain. Okay, but put these two things together. You can't see a 5-foot object 200 miles away, but you can see this huge mountain 200 miles away. But just because you can see the mountain 200 miles away doesn't mean that you can see the base of the mountain 200 miles away, and that you could see, so here, just read this last sentence. But could you see a 5-foot tall person at the base from 200 miles? Of course not. Of course you can't. And it's because, I mean, I can get into, I don't want to make this video too technical, but I do have my own theories about what's going on here. I guess I can just shout it out here. Basically what's going on is the closer you go to the horizon, there's just too much information there. There's so much stuff that's between you and the base of a mountain. Think of all the shrubs between you and the base of the mountain, all the slight variations in just the ground. Or, yeah, again, shrubs, trees, bushes. How many of these things are between you and the base of a mountain? That's why the base of these objects gets obscured. Same thing with a ship that's really, really far away. Why do you think that you should be able to see the base of a ship that's really far away? There's all sorts of little waves between you and the ship. There's a bunch of sea spray that's spraying up between you and the base of the ship. People just don't understand that when a really big object gets really, really far away, the base of that object gets obscured. That's just a property of vision. It's the way our eyes work. So I have a third law here, whatever. I think it kind of comes out of the first law and the second law. There is some fuzzing of vision at the horizon because the human eye does not have infinite resolution and we can't zoom in infinitely. So the reason that you can see a top of a mountain fine when it's really far away is because there's nothing between you and the top of the mountain except air. But when you look at the base of a mountain that's really far away, there's a fuzz. You get a fuzzing because there's just too much stuff. Your eye doesn't have infinite resolution. Your eye can't tell you exactly what's happening there. It's like there's an overload. Too much stuff. The eye can't see what's happening there. So, like many things, it's almost like an optical illusion where things get fuzzed near the horizon. So here's just another thought experiment. Again, go to a flat plane, an infinite flat plane. So here's something that we don't even live here, but we can have a thought experiment because Earth is finite. It's not infinite. So we have an infinite rail on a flat plane. Just because we have an infinite amount of rail, it doesn't mean that we see an infinite amount of rail. There's still a horizon line. So an infinite amount of rail fits in a finite area. Well, so we have some math stuff. What does this remind me of? Geometric series. Well, any series that converges, an infinite series. In mathematics, you can add an infinite number of things together and stay finite. Just what happens is the things that you're adding together need to be smaller and smaller. A half plus a fourth plus an eighth plus a 16th plus a 32nd. They need to get smaller and smaller and smaller. And that's how this vision thing works for me. Everything tends towards the horizon, but the problem is that you have less and less space to display it. When you're really, really close to the horizon, what's going on here is you still have an infinite amount of rail that you need to be displaying, but you have smaller and smaller area that you can display it in. So Again, your eyes don't have infinite zooming capabilities. Your eyes don't have infinite resolution capabilities. So you get some fuzzing where that happens. So I'll just read this. The things you're adding need to get smaller and smaller. The farther away the rail is, the smaller it is in your vision. Eventually the rail is smaller than, 1 pixel of your vision. Near the horizon, infinite amounts of information is needed to be displayed in a finite area. Coupled with atmospheric perspective, the horizon is often washed out. Here's your expectations on the left, but what's a reality? It kind of tends to look more like this and get smudgy. There's actually I should go try to find it and put it in the comments, somebody messing around with the P900, and even when they zoomed in with the P900, when they got really close to the horizon, funny stuff starts happening. Rails start to become looking like they're bent when they're not really bent. You get strange optical properties near the horizon. And just the simple way that I can just explain it for myself is, it's like your brain gets an information overload, so it just has to do its best to display something for you. And optical illusions are a big part of this place. The controllers, think of how much children's stuff. I remember when I was young, there was so much children literature talking about optical illusions and things on the internet. If something's an optical illusion, just think of how big stuff gets, like the dress. Oh, is it gold in this color or that color and that color? The Yanni Laurel stuff, that stuff is big for a reason. People get a real kick out of this. Illusions. It's an illusion. The top of a railroad doesn't start getting wacky and strange looking because it's going over a curve. No. This is just the way optics works. Near the horizon, you're trying to cram too much information into a small space, so your brain just does its best. Here's this beautiful picture. Look how flat. It's really, really obvious. Think of funhouse mirrors. Think of how obvious it is when a mirror is not perfect, when a mirror is curved. There's all sorts of jobs out there. A lot of quality control is humans. The human eye is very powerful. Not perfect. It doesn't have infinite resolution. It doesn't have distance. You can't see forever. But the human eye really can sense curvature very easily. One of the shows that I will watch is How It's Made, shows that talk about how things are produced. And very, very often you'll see it's a human in charge of looking over to see if there's any imperfections in, say, a mirror or a chrome bumper. They have a human go and look at it because it's very easy for a human to see if something's bent the wrong way. Look at your eyes. Do you see any curvature to this water, or does it look perfectly flat? It's perfectly flat. Perfect. Perfectly flat. Water finds its level. Look here. Oh, this is as far as I can zoom in on this picture. Man, the mountain way, way, way far in the distance. Can you tell? I should try to get another picture. Maybe I'll just do another video on this. There's a really fine white, it's the color of sky, kind of blue white, underneath, between the mountaintop and the darker line. So this is as far as this is letting me zoom in. Maybe I'll just have to add something later. Let's see if I have a better picture. Oh, I just have this. Well, here, we'll just talk about this. Notice, yeah, we'll end with this because this is perfect. This is the kind of thing that people use to, quote unquote, prove that it's going over the edge. But if it's going over the edge, why doesn't the top of the mast move down to the ocean? Look, it stays above the ocean. It's not that it's going over a curve and the masts are now at the base of the ocean. It just gets fuzzed. Look what's happening. The only thing that's happening is the object is getting smaller and the horizon is getting fuzzed out because the eye cannot tell what's going on there anymore because there's these little waves cresting up and it's blowing up sea foam, and there may be some sort of optical lensing going on, but I don't want to make this too complicated. But do you notice how the sails stay above the ocean? Even in the very last frame, you can tell they're above the ocean. They're not going over a curve. The base of the ship is just being obscured by basic optical properties. The earth is flat and unmoving. Praise Jesus Christ. Jesus Christ is the Messiah. don't be duped just because you don't think about how optics works and because you just haven't looked into it. You can clearly see that this is not going over a curve. It's just that the base of the ship is being obscured. God bless everybody. Hans Wormhat, just to finish this video off, just grabbed a few images. I zoomed in on this one. Look at how you can see the white line underneath that mountain. What, is that mountain supposed to be like floating or something? Why can't we see the bottom of it? Well, it's just what I've explained in this video. It's the same thing that stops you from being able to see the bottom of a ship that goes really far away from you. When an object is really, really far away from you, the bottom of that object gets harder and harder to see, it gets more obscured. And that's just the way vision works. Like, look, you can see the white line at the bottom of that mountain in the distance. That doesn't mean that that's the curve that we're seeing and the mountain is hiding behind it. It's just an optical property. It's how we view objects. Objects very far in the distance, the base of them get washed out even more than other parts. And there we go, that's it. I mean, you can see it happen twice here. At the very base, it gets white. Are these mountains floating? Floating over the curve? We're only seeing the part over the curve? Or does some of the mountain just get obscured? Is that just how optics works? That the base of objects very far in the distance get obscured. The base of objects very far in the distance get obscured. It's just a property of vision. There's no ball. You're not spinning through a vacuum. God bless everybody.